Perception is the set of process by which an individual recognizes, organizes and makes sense of the sensation he receives from the environmental stimuli. Perception encompasses many psychological phenomena. Visual perception is the most widely recognized and most studied perceptual modality. The existence of perceptual illusion suggests that what an individual senses is not necessarily what he perceives. Our minds must be taking the available sensory information and manipulating that information somehow to create mental representation of objects, properties and spatial relationships of the environments. Moreover, the way one represents these objects will depend in part on viewpoint in perceiving the objects. For millennia, people have recognized that what one perceives often differs from the rectilinear sensory stimuli that reach the sense receptors. Architects are not the only ones to have recognized some fundamental principles of perception. For centuries, artists have known how to lead us to perceive three-dimensional percepts when viewing two-dimensional images. Such stable perception occurs despite constant changes in the size and shape of what one observes. Vision begins with the light passes through the protection covering of the eye. This covering, the cornea, is the clear dome that protects the eye. The light then passes through the pupil, the opening in the center of the iris. Light then passes through crystalline lines and vitreous humor. The crystalline lens is a transparent membrane located behind the iris. This membrane can flex or relax to allow one to view objects both close and at a distance. The vitreous humor is a gel-like substance that comprises the majority of the eye. The major role of the vitreous humor is to provide support for the eye. This process results in the refraction, a change in direction and speed of the light entering the eye. Refracted light focuses on the retina, a network of neurons extending over most of the back surface of the interior of the eye. The retina is where electromagnetic light energy is transduced, that is converted into neural electrochemical impulses. Although the retina is only about as thick as a single page in a book, it nevertheless consists of three main layers of neural tissue. The first layer of neuronal tissue closest to the front, outward facing the surface of the eye, is the layer of ganglion cells whose axon constitute the optic nerve. The second layer consists of three kinds of interneuron cells. Amacrine cells and horizontal cells make single lateral connections among adjacent areas of the retina in the middle layer of cells. Bipolar cells make dual connections forward and outward to the ganglion cells as well as backward and inward. The Gestalt psychologists believe that brain creates a coherent perceptual experience that is more than simply the sum of the available sensory information, and that it does so in predictable ways. In one important facet of the perceptual process, one distinguishes figures from the ground against which they appear. A colorfully upholstered chair stands out from the bare walls of a room. A marble statue is perceived as a whole figure separate from the red brick wall behind it. Perceptual constancy is defined as a tendency to perceive objects as stable and unchanging despite changes in sensory stimulation. Without perceptual constancy, the tendency to perceive objects relatively unchanging despite changing sensory information. When objects are close to one another, one tends to perceive it together rather than separately. Most people would perceive these 7 lines as 3 pairs and an extra line at the right because of the relative proximity of the pairs of lines. Similarity. Objects that are of a similar color, size or shape are usually perceived as a part of pattern. Most people would perceive the first figure vertically as a columns of dots and dashes, not horizontally as a rows of alternating dots and dashes. Closure. An individual is inclined to overlook incompleteness in sensory information and to perceive a whole object even where none really exist. Here one tends to see a series of rectangles rather than a series of bracelets. Now let us see continuity. Items that continue a pattern or direction tend to be grouped together as a part of the pattern. In this figure, one tends to perceive a continuous wavy line crossing 3 square humps, even though the figure could justifiably be perceived as 2 separate lines. Characteristics of an observer. An individual clearly draws on past experience and learning when it comes to perception, but his own motivation, values, expectations, cognitive style and cultural preconceptions can also affect the perceptual experiences. Motivation also one of the factor. Often an individual desire and need strongly shape his perceptions. People in need are likely to perceive something that they think will satisfy that need. For an example, if people are deprived of food for some time and are then shown vague or ambiguous pictures, they are apt to perceive the pictures as being related to food. Values also affects. In an experiment that revealed how strongly perceptions can be affected by a person's values, nursery school children were shown a poker chip. Each child was asked to compare the size of the chip to the size of an adjustable circle of light until the child said the chip and circle of light were the same size. The expectations. Preconceptions about what an individual is supposed to perceive can influence perception by causing him to delete, insert, transpose or otherwise modify what he sees. People taking the field dependent approach tend to perceive the environment as a whole and do not clearly delineate in their minds the shape, color, size or other qualities of individual items. People who are field independent are more likely to perceive the elements of the environment as separate and distinct from one another and draw each element as standing out from the background. Cognitive styles can also be viewed from the perspective of levelers and sharpeners. Those level out of distinctions among objects and those who magnify them. Now let us see about experience and culture. Cultural background also influences people's perceptions. Cultural differences in people's experiences can also influence how people use perceptual cues. Historically, for an example, the Mupti pygmies of Zaire seldom left the Ituri rainforest and rarely encountered objects that were more than a few feet away. Perception of distance and depth. Visual cues requiring the use of one eye is called monocular cue, and visual cues requiring both the eyes are known as binocular cues. Perceiving depth and size. The problem of finding depth from two-dimensional retinal images is an underdetermined problem. However, the human eye achieves this great ease in almost no time. The first question to ask is what information contained in this two-dimensional image makes us perceive depth. This is called the cue approach. This approach focuses on identifying the elements of information in the two-dimensional scene that is related to depth of the scene. The depth cues can be divided in three different categories. Oculomotor, these are cues based on the ability to sense the position of the eyes and the tension in the eye muscles. Monocular, cues that work with one eye. Binocular, cues that depend on two frontal eyes. Oculomotor cues are due to convergence and accommodation. When looking at nearby objects, the eyes move inwards. This is called convergence, and when looking at faraway objects, the eyes move outward. This is associated with accommodation. When the eyes move inward, there is a tightening of the muscles that hold the lens to get the eye to focus close by. When the eye moves outward, muscles relax. An individual can sense both of these, which give an estimate about the depth of the object. One can experience this by moving an object at his arm's length closer and closer to the eye to feel the tightening of the muscles, and then move it back again to feel the muscles relax. Monocular cues are the ones that are obtained from the two-dimensional image of only one eye. These include occlusion. When one object is hidden fully or partially, this hidden object is considered to be further away. Behind object which is covering it, relative cues. The second cue is that of relative height. The objects that are further away have higher bases in the image. It will be shown in the figure. The three men in this figure are perceived at different depths, and the man with feet higher up in the image appears farther away. However, note the perception is entirely different for the clouds. Shadows. An example where the occlusion and the relative height cues contradict each other. In such cases, an individual depends on some other cues. Shadows provide very important depth cues. In this case, the presence of the shadow removes the contradiction by telling that the vase is in front of the glass but at a higher depth. Relative size. If two objects are equal in size, one that is farther away will take up less of the field of view than the closer one. This is called the relative size. However, note that this depends on the ability to recognize different parts of the 2D image as similar objects. Familiar size. The knowledge of sizes of objects can affect one's perception. This is called the cues of familiar size. For an example, familiarity with the size of the different types of coins is important in perceive the depth of the array of dimes and quarters in figure. Binocular cues depend on the images from both the eyes. The eyes are placed about 6 cm apart and hence they get a different view of the objects in the environment that appear in both the eyes. Since the frontal eyes, overlap of the view from the two eyes is significant, but the viewpoint is different. This difference is called binocular disparity and is converted to depth information. The information provided by the disparity is called stereopsis. The images of the same scene from different viewpoints of the two eyes are shown in figure. This revelation leads to design of several systems where depth perception can be generated. Such displays were called stereo displays. One popular approach was taken in cinema projection where differently polarized light was used to project the images from two different viewpoints on the same screen. The users were provided with glasses. The left glass allowed one direction of polarization and the right glass allowed the other. Thus, though the users were watching the same screen, two eyes received two different images. The right image was blocked by the left glass and vice versa. This created a compelling sense of depth. Similar technologies were used in head mounted displays where a headgear with two micro screens, one in front of the eye, is mounted on the head of the user. The images of scenes are generated from two different viewpoints and projected on the two different screens to create a compelling sense of depth. Corresponding retinal points are the locations in each retina which connect to the same place in the visual cortex. One can determine these points by locating the matching points on the retina when one retina could be slid on top of another. Figure shows the corresponding points A and A0, B and B0, F and F0. When one fixates at point F shown in figure, all the points lying on the circle defined by F and foci of the two eyes are imaged at corresponding points in the two eyes. This circle is called the horopter. In this example, one can show the eye of lifeguard who is watching a bunch of kids in the swimming pool. Ralph, Harry and Susan are on his horopter and hence their images are at corresponding points of the two eyes. In case of Charlie and Carol, who are closer than the horopter, note that the images of these points closer than the horopter do not lie on corresponding points across the retina. For example, Carol's image on the left eye and right eye are at B and G0 respectively. The angle between B and corresponding point G in the left eye is the same as the angle between B0 and G0 in right eye. This angle defines the disparity of a point. Note that as the distance to an object within the horopter increases, the images move away near the sides from the image of the horopter. However, if the objects are beyond the horopter, as the distance increases, the images move towards the inner part of the eye. This information, in addition to disparity, helps us to decide whether the object is within the horopter or beyond it. Perception of size depends closely on perception of depth. If the size of an object in retinal image B R, the depth of object D and the focal length of I, the perceived size S is related to these by similar triangle equation. S divided by R equal to D divided by F. S equal to dr divided by F. This was also demonstrated by a very effective experiment. The experiment setup and the results are shown in figure. A person was positioned at the junction of two always. A comparison pattern was in front of him. On his right was a test circle. The size of the test circle was increased proportionately with its depth as per equation, so that the size of the retinal image remains the same. Then he was asked to change the size of comparison circle to match the size of the test circle he perceives. The size of the test circle in the retina remained the same. The size was changed with depth to keep the retinal image same. The right image of figure plots the perceived size of the test circle with its distance from the viewer. The slanted dashed line shows the actual change in size of the test circle, and the horizontal dashed line shows the size of the retinal image, which is constant. Line 1 shows the subject's perception when all the depth cues were present. This shows that though the retinal size is same, the user can make use of depth cues to perceive a size that is close to reality. Line 2 shows the results when one of the subject's eye was closed, that is, when binocular cue was absent. Line 3 shows the perceived size when the subject was looking through a peephole, so that all monocular cues are absent. Line 4 shows the response when the walls were covered with drapes, so that there are no shading cues. Size perception affects the veridical experience and works well in well lighted natural environments. However, if conditions are adverse, some pathological cases can be designed where the size perception can falter. The left image of figure shows that the vertical line of the left figure looks shorter than that of the right figure, though if one measures them with scale they are the same. The right image figure is one possible explanation. These two lines represent an outside and inside corner respectively. Since the depth of the inside corner is more, one tends to perceive the line as longer following the equation. However, note that this explanation cannot explain the three-dimensional Muller layer illusion that can be easily constructed by a couple of books. Here, even though these are not perceived as corner, one perceives the space between the left one to be smaller than the right one, though when measured they are the same. The second explanation that seems more plausible is that of conflicting cues. This says that the perception of the length of the lines depend not only on the actual length of the figures, but also on the overall length of the figure. If the overall length of the figure is more, one tends to perceive the line as longer. This is further strengthened by another example of this illusion in figure. The distance between the 2 points in the right image are same for both A and B, but one perceives one as longer than the other. Figure shows the bonza illusion. Though the two white lines have same size, the one at the top appears longer. This is explained by the fact that the perspective projection provides us with a strong cue for depth, which tells us the upper line is further away from the bottom one. Hence, one perceives a longer line as per equation.